In 2017, John Rakovan and I published an article in Rocks and Minerals highlighting some of the world's finest wire silver and gold specimens. What is perhaps most striking about the wire habit are the strong longitudinal striations, giving them an appearance which resembles locks of hair. For silver, the wire habit is uncommon, though they can be found in a wide variety of deposits around the world. For gold, on the other hand, true examples of the characteristic striated morphology are rare, and are known from only a handful of locations. Given that we have only recently begun to unravel the origins of wire silver, it's not surprising that a very little is known about the growth of wire gold. The uniqueness of the wire habit has led us to hypothesize that wire silver and wire gold form by a common process. Therefore, we will consider what our recent observations of wire silver growth can tell us about the origins of wire gold. Over the last several years, we've collected a suite of natural wire silver specimens from around the world, and also grown a significant number in the laboratory. As some of you are aware, wire silver can be grown simply by heating the mineral acanthite, which is silver sulfide, to above 450 degrees Celsius in a strong thermal gradient. This works in virtually any atmosphere, including air, and even in a vacuum. Here's an example of what my growth experiments look like. This produces wire silvers about a centimeter long in about an hour, fast enough to observe their growth in real time. Comparing the textures of natural and synthetic specimens revealed that wire silvers in general are polycrystalline aggregates, and that the striations are merely superficial features. These are scanning electron micrographs of representative natural and synthetic wire silvers. If you look closely, you can see the grain boundaries expressed at the surface. We've also analyzed the bulk crystallinity with energy-resolved neutron resonance imaging, which confirms the textures we observed at the surface. In some specimens, there can be a small degree of preferred crystallite orientation, but overall, crystallites can be found in virtually any orientation within a given specimen. While looking at acanthite under the scanning electron microscope, I observed the initial stages of wire growth in real time in vacuum. This time lapse represents about 30 minutes. The lighter colored material is native silver. You can see that as the blooms increase in size, they become raised up on little pedestals. It turns out that while acanthite is an insulator, its high-temperature polymorph argentite is a superionic conductor. Actually, it has the highest ionic conductivity of any known material, natural or synthetic. Shown here are selected portions of the acanthite and argentite structures, respectively, where yellow atoms are sulfur and gray atoms are silver. Argentite possesses a high degree of dynamic disorder, which can only be approximated by using a large number of partially occupied silver sites, as shown here. This phase transformation occurs at ambient pressures when the temperature reaches about 180 degrees Celsius, and results in about a 3% volume change, with argentite having the greater volume. In nature, oftentimes crystals of acanthite are seen in octahedral forms. These are actually acanthite paramorphs after argentite, which recrystallizes into acanthite at low temperatures. Based on the unique combination of texture and morphology, combined with the observations in my growth experiments, and informed by the unique properties of silver sulfide, I proposed a growth mechanism for wire silver. The wire silver morphology can be explained by base growth via a local phase transformation of acanthite into argentite, which then acts as a portal for solid-state ion conduction of silver plus ions. However, the external morphology is constrained by the shape of the footprint. Thus, as more silver atoms are added to the base, the wire extends up from the surface, and the striations are propagated, resulting in the characteristic morphology of wire silver. We published this model in the journal Geology last year, and it was even featured in the cover photo for the July issue. But now, what do we know about the growth of wire gold? In 1919, Butel published a paper called Growth Phenomena of Copper, Silver, and Gold, in which he attempted to grow wires from silver, copper, and gold, sulfides, selenides, and tellurides. They found that gold chalcogenide compounds were too unstable at high temperatures to grow wires, and heating them only resulted in subliming the chalcogens. However, they noted that if a gold-silver alloy was used, they could grow wire gold in the same way as wire silver. Given that the wire habit seems restricted to the coinage metals, that by far the most common among these are wire silvers, and that gold wires have only been grown when gold wire alloys are used, we hypothesized that something about the presence of silver is critical to the development of the wire habit. And therefore we predicted that all true wire gold specimens, those which clearly exhibit the characteristic striations, will be found to contain a significant proportion of silver. To test this prediction, we used energy dispersive X-ray spectroscopy to measure the elemental abundances in wire gold. The way this method works is that a sample is bombarded by an electron beam, promoting some of the electrons in the material to excited states. When they relax, they release a characteristic X-ray, which has a specific energy depending on the exact orbital transition that takes place. These energies are element specific, allowing us to quantify the amount of an element in a given material. So far, we've analyzed 4 specimens, the first of which is this specimen from the Groundhog Mine in Eagle County, Colorado, and the remaining 3 are from placers in Bolivar, Venezuela. You can see that the placer wire gold on the right has a greenish hue, suggestive of high silver content. And here is a table of the EDS results. Considering the 4 specimens we've analyzed, wire gold appears to contain at least 35 atom% silver, and in the case of VEN1, up to almost 75%. Not only are these silver concentrations consistent with our prediction, but they're even greater than what we expected. For instance, our results indicate that these 2 specimens have an identical silver content, about 38 atom%, despite the fact that one of them is greenish and the other is not. Although we need to conduct more analyses to confirm our hypothesis, these results are entirely consistent with the idea that silver is critical for wire habit growth, even in wire gold. We might expect then that perhaps wire gold grows by a very similar process to that of wire silver, namely via solid-state ion conduction constrained by a phase transformation footprint. At this point, we've not yet identified a gold ion conductor in nature, though we do have some hints as to where to begin looking. In the 1978 report on the geology of the Gilman district in Colorado, which contains the Groundhog Mine, Lovering et al. Notes that occasionally pockets rich in telluride ore were found in the area. The authors go so far as to suggest that even though only one such pocket was reported in the Groundhog Mine, that perhaps there were other, quote, undetected telluride minerals, which would better account for the concentration of gold in the deposit. Given the almost singular uniqueness and exceptional nature of wire gold specimens from the Groundhog Mine, we expect that its substrate is likely a very uncommon mineral. Shown here are selected portions of gold-silver telluride minerals. When comparing their stoichiometries and structures, you can see that as their overall silver content increases, disorder also increases. Noting that the silver content we've observed in wire gold falls in a range of 38 to 72 atom% silver, we suspect that one of these moderately silver-rich minerals, such as krennerite, sylvanite, or petsite, may possess undocumented ion conduction properties, or perhaps a high-temperature unstable phase which does. While this remains speculation at this point in our study, it would make sense that as the gold and silver content of an unstable ion conductor would become depleted, that the residual mineral would not preserve the ion-conducting structure. This would explain why such a hypothetical ion-conducting gold-silver telluride has not yet been identified.